Hello students, once again you're welcome to Network Essential Management class in Waidsum University. Today we're looking at chapter 7 part 2, the router fundamentals. Quickly we want to look at some fundamentals that has something to do with routers. Okay, so without much ado, let's begin. Now the first part is the introductory part of the fundamentals of router. So here, this section, we're going to in this section we're going to further define the functions of a router. Okay, we want to look at, in this case, we want to look at the functions. Or first of all, define the router itself, and define the functions of the router in the network, and we're going to also look or describe the data packets that travels through a layer 3 network. You know, we said routers are used for layer 3 networks. Okay, switches and hubs are used for layer 2 networks. So routers, they're practically used for layer 3 networks. Now a layer 3 network uses an IP address, right, to route any data packets to a given destination, to any destination that the data packet is designated for, that is meant for. That's what a layer 3 it's used for. A layer 3 helps to provide that routing protocol by using the IP addresses to route data from their source port to the destination port. Okay, now let's quickly take a look at another things that happens within the fundamentals of router. While we're looking at the fundamentals of router, another thing to look quickly is the delivery of the data packets. The delivery of the data packets over the layer 3 network is made possible by use of 4 things. Now, what are these 4 things that we need to put in place in order for us to be able to deliver the data packets to the destination place? One of it is you need to know the MAC address that the router is going to, you know, when we get to the router gateway that leads to the destination, that gateway quickly issue an ARP, address resolution protocol, to the host to the destination MAC address of the computer. And once it's established, the ARP is established, then the router will forward the data packets to that designated computer. Okay, so using a routing table. So one of the very things that we need in whenever we deliver a data packet over a layer 3 network is, or one of the things that out of the 4 things that makes it possible, one of it is the destination MAC address. So we need to know the destination MAC address of our computers, of the computers that we are sending the data packets to. Number one. Another thing we need to know in order to deliver data packets across networks using layer 3 level of networks is the IP address. So we need to know the IP address, because when we send a data packets from a given LAN, a given local area network, it's going to find its way through a gateway address. So find its way to the router, and when it gets to the router will route it using the routing table to the destination. On getting to the destination, the data packet will land on the router in the destination gateway. So when it gets there, the router in the destination gateway normally will issue an ARP to the switch or the destination. So once that is established, like, okay, this is the destination is on this network, then the router will forward the data packets to that network, that local area network, where it's virtually the local area network establishes the MAC address, because the MAC address, the ARP, the address resolution protocol of the router, helps to establish the MAC address of the destination. Once that is established, then the router forward the data packets to that MAC address on the LAN. Okay, so another thing to note, apart from the MAC address and the IP address, another thing that helps us in the delivery of data packet across network is the network addresses. So every network has its own address within that segment, within the local area network, has its own address within the local area network. So once this is established, The fourth one is the routing table, because the router make decision using their routing table. The router make decision using their routing. So these four things are what are the very primary things that are required in delivery the data packets across a layer 3 networks. Okay, now let's move on. Each of these concepts we're going to look at, because each of these concepts form this chapter that we are talking about. Okay, each of these concepts holistically explain we holistically explain this chapter. Now, if you take a look at the diagram, what we have here, or the picture you have here, you can see different floors of a building. You can see the first floor with all the computer connected horizontally like this, and you can see a second floor, and we can see a third floor. Each of these are connected to their own switch. Presumably, each of the floor has its own switch to connect small local area network. So within this one building, you have, like, let's assume that we have the first floor has its own small local area network, LAN. You can call it LAN 1, or because it's in floor 1, and then the second floor has its own small local area network, and we can call it LAN 2, and then the third floor has its own small local area network, which we can call LAN 3. Now, each of these small LANs can be interconnected to form a big LAN. Each of these LANs can be interconnected to form a big LAN using switches. Using switches, we can interconnect each of these LAN to form a big LAN. Is that okay? So this is a different small local area network in a given building. Now, LAN sizes are not necessarily restricted in size. You can have many computers, like 10 computers in a LAN, 20 computers in a LAN, even up to 200 computers in a LAN, or even more. You can have up to 500 computers in a LAN. There's no restrictions to the number of size of computers you have in a LAN. So you can actually have a small local area network, like the small one we have in small campus or small colleges or small office areas. Like those ones you have, they like small LAN. But if you have a big campus, like has more than one building, or that has even if it's one building, has different floors, so many floors, okay, then you have to interconnect each of the small LANs to bigger LANs. So here you have so many computers in this large local area network. So you can have up to 200 computers in that LAN. So this is a big local area network if you have so many computers as such. There can also be multiple LANs. You can interconnect them by using that essentially creates one large LAN. So you can, like we have here, you have one small LAN, another local. Every floor has its own local area network, but we can always interconnect them using switches. You can use switch to interconnect them, as we've shown in this diagram. Okay, now we say, we ask a very sarcastic question here. We say, is it bad to interconnect LAN this way? To interconnect, you see this kind of horizontal connection? Is it bad? It's not the best, but still is possible. Interconnecting LAN like this is possible. It's not the best way to interconnect LAN, okay? Because if one breaks down, it may restrict the data being sent to the other computer, okay, on the LAN. So connecting like this, it's not the best topology to use to connect our local area network, right? But it's also possible. It's not like it's not doable or possible. Now, as long as it's not bad, but as long as this is when you can maximize or optimize the network, as long as switches are being used to interconnect the computers. So if you use switch, then the connection like this is not bad. If you use hub, then it complicates the problem. Okay, but if you use switches to interconnect the computer in this manner, then it's possible. The impact of the interconnected LAN has minimal impact on the network performance if you use switches. So if you use switch, then the negative impact will be minimal, will be smaller, when you're using a hub. Okay. Now we say this is true as long as there are not too many computers in the LAN. So if you're connecting computers like this horizontally in like in a bus topology, then we say you have to minimize the number of computers in that small local area network, as in every floor here. So if you want optimization, then you minimize the number of computers that you connect in this way. Okay, if you want optimal performance, you have to minimize the number of computers that you connect in this way. If you make them too many, then you will not get the desirable result, as it were. The number of computers in the LAN is an issue because layer 2 switches do not separate broadcast domain. Layer 2 switches, they do not separate broadcast domain. Or like the layer 3 switches, like the routers. Routers are layer 3 switches. Okay? So the layer 2 switches do not separate the broadcast domain. Now let's take a look at broadcast domain. Since we've mentioned broadcast domain, what do we mean by broadcast domain? Broadcast domain means that any broadcast set out on the network, like for example the broadcast associated with ARP, that's the address resolution protocol request that the router always send to the destination MAC address. Okay, and then that we say whenever an ARP request is sent, it will be sent to all the computers in the LAN. So we say broadcast domain means that any broadcast set out on the network, like the broadcast associated with ARP request, will be sent to all the computers in the LAN. So if a router has a data packet that has been sent, and the router is about to deliver the data packet, then the data, remember the router always issue the address resolution protocol. He always sent it to the MAC address of the different computer in that local area network. So if the ARP, the router, if the router issues this ARP, that's address resolution protocol, this ARP will be sent to all the computers on the network. That's the meaning of broadcast domain. To broadcast it to all the computers on that local area network. Okay, that ARP, address resolution protocol, will be sent to all the computers in that local area network. Excessive broadcast, they are a big problem in a network, but router will always broadcast. Router will definitely broadcast because it's always receiving data and it has to forward these data packets. Router don't necessarily have to keep this data packet because the router themselves, they are not destination. They're just happy to route forward data packets that have been sent or that have been sent to other networks. So what the router does, every time it receives, it has to issue an ARP to ask which of the computer on the receiving side has this MAC address. Once the MAC address is the media access control. Once any computer say, "Oh, okay, I'm the one," then that router will forward it to that same computer in that network. Okay. Excessive broadcast is a problem. Why? Why is excessive broadcast a problem? Because it will slow down the computers. The processing time of computer will slow down. Okay, the processing time of computers will slow down. The processing time of computers will slow down. Okay, so that's why it's a problem. So we need to optimize this problem because routers will always forward any broadcast by issuing an ARP request and sending it to MAC address of all the computers on the host, all the computers in the destination site. So this result to what we call a broadcast domain. So meaning all the computers will keep receiving, even if the data packet is not meant for you, even if the message is not meant for you, the data packet that is being sent is not meant for you. You keep receiving like requests. Are you the owner of this? You have to make a decision using your MAC address. If it's yours or if it's not yours. Then if it's not yours, you let the network know, no, this is not mine. So it forward it till the computer with a MAC address that owns that data says, okay, this is mine. So every time you be disturbed, so your processing time is essentially slow. So it slows down the computers in the network. The big disadvantage of this broadcast domain, the big effect, the big impact it has, is that it slows down the processing time of all the computers on a network. Is that okay? Now let's talk about the flat network. A network with multiple LANs, it are connected together at layer 2, is called a flat network. A network with multiple local area networks interconnected together at layer 2 is called a flat network. Like we've seen, now we have 1, 2, 3. We interconnect them to form a new network, and this new network is called a flat network. A flat network is where the LANs share the same broadcast domain. All the LANs in the system will share the same broadcast domain. The use of a flat network should be avoided if possible. Why? One of the reasons why we should avoid using a flat network is that the network response time is greatly affected. So there is a slowdown in the processing time of all the computers on the network. So we should find a way to connect computers in a network without doing a flat network. Flat network slows down computers' performance ultimately in a network. Flat networks can be avoided by the use of layer 3 switches. This is one way we avoid the flat network. Once you use a switch, once you use routers are layer 3 switches. We call them layer 3 switches. Okay? Once we use router, then we can avoid this interconnectivity that results to a flat network, because flat network slows down the processing time of all computers on a network. Now that leads us to layer 3 networks, which are routers. So like the small office that we normally have, or in our home where we have Wi-Fi, the type of local area network, in case we connect so many things to it, like our computers, our phones, our printers, whatever we have in our homes or in our small office. We remember we covered this in chapter 1. All of this, they are in layer 2 networks. They are just layer 2 switches. Okay, they are layer 2 switches. And the one we are describing now, where we have building LAN, different LANs connected in a building, and then the small LANs are interconnected together to form a larger LAN. Then this will lead us to what we call the layer 3 switches. The hosts are interconnected with a hub or switch. These allow data to be exchanged within the LAN. However, the data cannot be routed to other network because there is no router. So if you look at this building, there is no router. Everything is within this. All the data can be interconnected or be broadcasted within this building, whether in the first floor, second floor, third floor. Everything will be within here. All the data packets can be sent among themselves within the same network. However, if we decide to forward this from this building to other building or to other campuses or to other offices, then we need a layer 3 networks. This leads us to layer 3 networks, which are called the routers. Now, the broadcast domain of the LAN for this LAN is not isolated from another LAN's broadcast domain. So the solution for breaking up the broadcast domain to provide network routing is to incorporate the routing hardware in the network design to create a routed network. So here, the broadcast domain of one computer cannot be isolated from the broadcast domain of all. So you broadcast any day, it goes to all the computers. So any broadcast, they are not isolated from each other. If we want to do that, to isolate the broadcast domain from being broadcasted to all the computers in the network, then we need what we call a routing device to provide a routed network, which is called layer 3 network. Routed networks are called layer 3 networks. Okay, so a routed network uses the layer 3 addresses for selecting the different routes to forward the data packets to. So another name, or a better name that we can use for routed network, is called the layer 3 network. Is that okay? Now let's move quickly for the sake of time. Now we say in layer 3 networks, routers and layer 3 switches are used to interconnect the network and the local area networks. Okay, so basically whenever we talk about layer 3 networks, we are talking about routers and hopefully layer 3 switches. Okay, there are some switches that are called layer 3 switches. Layer 3 switches and routers are the interconnected devices that we use to create this and avoid so as to avoid the flat network. So every time and any time we want to avoid the flat networks, we need the layer 3 switches, or we need a router to create this, and so that we can isolate the broadcast domain. Because if we do not isolate the broadcast domain of one computer to the rest, then this will keep broadcasting anything. One computer will broadcast anything and every other computer gets it, and this, like we said, slows down the processing time of the devices in the network and eventually slows down the network, the entire network. So when we use a router or layer 3 switches, this will help us to isolate the broadcast domain. This is one of the big objectives why we need a router or why we need a layer 3 switch. Okay, not just the normal layer 2 switches. Why we need a router or a layer 3 switches is because we want to isolate the broadcast domain. And another function or use of layer 3 network is to enable the host of the different LANs and networks to exchange data. So because if you don't have a router or a layer 3 switch, you will not be able to forward the data from your local area network to any other network. You will not be able to forward any data packet from your local area network to any other local area network. In order to be able to forward data packet from your local area network to any other local area network that is not within your network, you need a router. You need a layer 3 switch or a router. Data packet delivery is achieved by handing off the data to adjacent router until the data reaches its final destination. So what you normally do when you have a data packet, first of all, is to deliver it to where it's going to. And to achieve this, you have to use routers. Okay, you have to use routers. And until the data reaches its final destination, then you have done the job. The job is done. Typically, it incorporates the passing of data packet through many routers and networks. Now, if I'm sending anything from Kuala Lumpur and the data packet is going to, let's say, Johor Bahru in Malaysia, or if you're sending something from Vancouver in Canada to maybe Toronto in Canada, and then you see the data packet might pass through series of routers before it eventually gets to the destination of the router where that interconnects to the network where the data packet is to be delivered. And once if that is established, the router will issue an ARP, address resolution protocol, to the network's MAC address. Any of the MAC address will respond and says, okay, I'm the guy who is supposed to receive this packet. Remember, the destination MAC address are inscribed by the system that is forwarding it, in the host that is forwarding it in the first place. So the destination MAC address has already been inscribed on the data packet. So once ARP is sent and a MAC address that holds it in the destination location establishes a connection, then the data will be forwarded from that router to the MAC address. That's the computers that holds it. Is that okay? So these are a bit of connection. This is a router gateway. All these are gateway. All these are gateway. Now you can see we can connect router to a router directly. This is a router A, router B, router C. You can see we connect from router A all straight to router C using this IP address, using this gateway address 10.10.100.0. And you can also connect from this router A to router B using 10.10.200.0. Okay, and then these are the IP addresses. Okay, you can also connect from router B to router C using 10.10.150.0. Okay, so these are the IP addresses. Now from here to this local area network with a switch, layer 2 switch, you can see that we have also an IP address 10.10.20.0. okay, and similarly every other one has its own IP address with which it connects from router to this switch, to this local area network. But from within the switch or from the switch to our computers, each one of them has its own unique network address. Each one of them has its own unique network address. Is that okay? Each one of them, for example, if you look at this computer, we have two computers here, computer 1 and computer 2 in this local area network A. If you look at this LAN A, we have computer 1 and computer 2 connected to this switch. Okay, computer 1, the IP address is 10.10.20, sorry, the network address is 10.10.20.1 for this A1. And for this one is 10.10.20.2. So these are called network addresses, but these are called the IP addresses, okay, from between the ones that create segments. You see, we have segments. These segments have their own IP address. Every IP address helps you to create segments, okay, in a network. Okay, so for all of them, we have this similitude. So here we have what we call the default gateway address. The gateway address is actually the IP address of a networking device, okay? Or your networking device is a router, okay? Most of the time is a router. Okay, so the IP address of your router is called the default gateway address. So we need to enter our default gateway address anytime we are programming networking. Okay, and the network or the gateway address is used by the LAN, the local area network, to forward the data packets to the router. They must establish the gateway address so that they know which gateway they're passing the data packet through. You know, the router is just like a media to help you carry it's like a carrier to help you carry your data packets from the host to the destination location. So you need to establish from the local area network a gateway needs to be established between the LAN and the router, and that is called a default gateway. Now, if you open your Ethernet protocol for your TCP/IP properties when you're programming, when you're configuring your routers, your IP addresses, you see here you put under your IP address, you put the IP address of that particular local area network, okay, of the network address, the IP address, and then the subnet mask 225.225.225.0, and then you put also insert your default gateway. That's which router is this one going first. Your default gateway is 10.10.20.250. So that's the default gateway address that this is. Once this is done, you click OK, and then you would proceed. So this LAN, by then these computers or this local area network is already established with this. Once you configure this like this by entering this information on your software protocols, then you will be able to establish a communication between this LAN and this gateway, this router gateway. Okay. Now let's take a look at because this one example covers for all is same similitude. Okay. Now let's take a look at what we have. If you take a look at what we have three routers here, and we have LAN, right? We have local area networks, and this router connects to. Now let's begin to describe. We have a gateway. A gateway is this space where this data packets can find its way to the router. These are local area network where you have a switch, and then we say that the data enter through the LAN like this, through the local area network from the router, and the data exits the local area network to the router like this. Okay, this is how it goes. But this interface are called the gateway. They are called the router gateways. They are called the router gateway. The term gateway is used to describe the networking device that enables data to enter or to exit a local area network. Gateway is used to describe the networking device, which is usually a router, a device that enables data to enter and exit a local area network. Okay, so the gateway is where the host computer forward data packet that needs to exit the local area network through to the LAN. Okay. Most network, the gateway is typically a router, like we said, or switch port address. Most gateway, in most networks, the gateway is usually a router or a switch port address. An example of a gateway is provided in a block diagram that you've seen. Now let's take a look at an example solving a problem. Let's see this example, how to establish whether a given data packet needs to leave a particular network to any other destination or needs to be forwarded to another to a computer on the same network. Now here is the example. A computer host sends two data packets out on a network. A computer host sends two data packets out on a network. Now each data packet has a different IP address. Each data packet has its own IP address, different IP address. Now determine if the data packets are to be forwarded to the default gateway or it should remain in the same LAN as host. So we need about three basic informations here. We need to know the source host IP address. we need to know the subnet mask, and we need to know the destination IP address. So in order for us to establish whatever calculation we need to do. Now here are the information. The source host IP address is 10.10.20.2, and the subnet mask is 225.225.225.0 that is being used. Then the IP address for the data packet, the destination IP address for the data packet is 10.10.11.1.1 and 10.0.20.3. Now let's solve this problem. We first of all have to solve for the source host. We have to solve for the source host before we do the destination, and see whether it's going to remain in the same LAN, whether the data packet that we are about to forward, whether it's being forwarded to a computer on the same local area network, or is forwarded to a computer on another local area network in another location, in another destination. Now here is the, first of all, the source IP address, we write it down, is 10.10.20.2. Then we go to add it to using AND gate logic. Okay, we go to add it by using the subnet mask. Now 225.225.225 means it is completely exhausted. So 10 plus this, you get 10. This one is used already, no space. So you get 10. Then 10 plus 225 again, you get 10. In the logic gate, the way we add 20.225, you get 20. Okay, because this one is filled, all the space filled. Now 2 plus 0, you get 0, because there's no space, nothing is being used here, you get 0. So this will be the source host is in the 10.10.20.0 subnet. The source host has this subnet 10.10.20.0. Now we go to calculate for the destination host. If the destination host has the same subnet, then the data packet will remain in that network. You know, be forwarded to a computer on another local area network. But if it's different from this, then it's going to be forwarded to a computer on another local area network, not on this local area network. Now let's see the destination for two, because they gave us two destinations. The first one, destination IP address for the first one is 10.10.1.1. So you add it to our subnet mask. So 10 plus 225, you get 10. 10 plus 225, you get 10, because it's completely exhausted. This one is filled up. 1 plus 225, you get 1. 1 plus 0, for this one, you always get 0. You can see this subnet. You see this subnet is completely different from the source subnet. Let's see. The destination subnet address, this one is a destination subnet. This destination subnet address, okay, 10.10.2.1.0, is not the same as the subnet of the host. It's not the same. You know, for the host, we got what? For the host, we got 10.10.20.0. For the host, we got the subnet for the source IP address. The subnet was 10.10.20.0. Now for the destination, for this particular destination, we got 10.10.1.0. So it means that this data packet, because of this subnet that we've calculated, this data packet will be forwarded to a computer in another network, in another local area network, okay, to be forwarded. Now let's take a look at the B part. You say the B, we write the IP address, destination IP address, 10.10.20.3, and then we always add the subnet mask 225.225.225.0. Now 10 plus 225 we get 10, 10 plus 225 we get 10, 20 plus 225 you get 20. 3 plus 0 you will get 0 in this regard, because there's no any mark on this subnet mask. There's no mark, so you get 0. Now you can see that this 10.10.20.0 is same with the source. It's same with the source. You can verify that by checking the source. Come and see the source. The source was what? The subnet for the source is 10.10.20.0. Now if you look at this destination we've calculated, it's also same as 10.10.20.0. So what this means is that this computer, this data packet is not leaving, this local area network. It's going to be forwarded to a computer on this same local area network, since it has the same subnet with the source, source host. So it's not leaving this local area network. It's going to be forwarded to a computer on this same local area network. Is that okay? Now let's move on quickly. Next hop address. The IP address of a data packet sent from the source computer to the gateway is examined by the router first and foremost. It's going to be the IP address of the data packet will be examined by the router, and then a next hop address is selected. So once the router examines, he knows okay where the data packet will be going. So he will select the next hop address. The gateway examines the IP address, the destination IP address of all the data packets arriving at its interface. So the router uses a routing table to determine whether the data packets or the next hop address. So the router will eventually use the routing table like we established at the beginning of the class, that the router uses a routing table to determine where the data packet is going. So the router uses the routing table to determine a network path, a network data path, and the next hop address that the data packet will be routed to or will be routed to. So a routing table is a list of possible networks that can be used to route the data packet. So a routing table contains the list of all the possible networks that can be used to route the data packet based on the destination. Okay, now let's take a look at the alternate data path. Alternate data paths are usually provided so that a new route can be selected and the data delivery maintained over if a network is down. Okay, alternate from the word alternate is another route that you create just to help you in case the network is down. So you can use that route to route the data to its destination. Okay, that's what we mean by alternate data paths. Now the next hop address is the IP address of the next networking device that can be used to forward the data packets to the destination. The next hop is the IP address of the next, not the original router, the other router where the data packet is going. So the IP address of the data of the router where the IP address is called the next hop IP address. Okay, so for example, if I forward the data from this local area network A to this IP address through this gateway, then the router routes this data packet to router C, and then establishes that this will be going to LAN D and the computer is D1. Once this one send the ARP address resolution protocol, and this one forwards it to these two computers, then they establish the MAC address of this computer. We say, okay, I'm the one that owns the data packet that was being forwarded from A1. So D1 we establish and say, oh, it's for me. This data packet is mine. And then this one will notify the router, then the router will forward the data packets to D1. Okay, so this is what is happening. Now let's take a look at the MAC addresses. First of all, MAC addresses are called media access control, and they are found in every computers, and they are used to, your computer has network interface card, and then the MAC address is used to establish a destination where the data comes, or a source where the data is leaving from. The MAC address are used to define the hardware address of the next hops in the network. They also used to determine the MAC address. They are used to define the hardware address. The hardware address, that's the computer. The hardwares are the computers now. To determine the hardware address of the next hop in the network. The term next hop refers to, next hop means the next networking device that is being used to relay the data packet to either an intermediate hop or possibly to the final destination. Okay, once this is done, once you have established the next hop or you've defined the next hop, the MAC address of the next hop is determined and the data packet is relayed, that is forwarded to where it's supposed to go. Once the route are fully configured, the data packets can be exchanged between any LANs in the interconnected routed network. Okay, so let's move on quickly. Now let's talk about segments on a LAN. A segment in a network defines the physical link between two interconnected devices. A router, it could be a router to a router, it could be a physical link between a router and a router, that's what we call a segment. Or you are talking about a router and a switch, that could be a segment. Or a router and a hub, that could be a segment. For example, in an interconnected network, a segment is the name of the link between a router and another router. The link between, the name of the link, like, you see, this is a segment. See, this is the link between this router and this router. So this is a segment, And also this is a segment because it's between these two routers. This is a segment, okay? And this is also a segment because it's a link between a router and a switch, okay? This is, all of these are segment, a router and a switch, okay? So that's what a segment is. Another example is the segment that contains or that connects a router to a LAN via a hub or a switch. Okay, we have already explained that. Now let's move on quickly. Here is a segment. Okay, you can see this red highlighted. This is a segment connecting a router to a router. This is another segment, a router to a router. This is another segment connecting a router to a router. Then here again we have segment connecting router to local area network, to switch or hub. Okay, all these four, look at this four: router to a hub or a switch, router to a hub or a switch. These are also segment: router to a hub or a switch, router to a hub or a switch. Okay, each one has its own network address or its IP address, as the case may be. Then after that, we now talk about the LAN. The LAN also connects to different computers. The LAN also connects to different computers. For the small campus network, the network IP address for the segment connecting LAN A to router A is 10.10.20.0. All the hosts connected to this segment must contain 10.10.20. Maybe 1, 10.10.20.2. Any computer on this network will have this IP address: 10.10.20.1, 10.10.20.2, 10.10.20.3, like that, depending on the number of, as you align the computer or arrange the computer. Okay, so for example, computer A1 will be 10.10.20.1 because it's the first computer on this local area network. Okay, so let's go talk about subnet. The segment is sometimes called the subnet. A segment, you know, we've talked about segment. We say router, between a router and a switch is a segment. We say between router and router, the physical link layer, the physical link is called a segment. Between a router and a router, between a router and a LAN, or between a router and a switch, they are called segment. So segments are actually called subnet. Segments in a network is what we actually call subnet or net. We can just simply call them net, or either we call them net, net, or we call them subnet. So every segment is simply called a net or a subnet. These terms are associated with a network segment address such as 10.10.20.0. In this case, the network is called the 10.10.20.0 net. Okay, all the computer connected here, we start taking this number 10.10.20.1, 10.10.20.2, 10.10.20.3, like that to 4, 5, 10.10.20.5, 10.10.20.6, like that. Okay, that's how this one rolls. Okay, now let's talk about the physical layer. The physical layer interface. The physical layer interface on the router provide a way to connect the routers to other networking devices on the network. Could be to connect the router to another router or router to switches. For example, the Ethernet ports on the router are used to connect to other Ethernet ports on other routers or to other switch. The fast Ethernet and the gigabit Ethernet ports are available on routers to connect to other high-speed Ethernet ports. Routers are also contain serious interfaces that are used to interconnect the router and the network to other serial communication devices. Okay, they also have serial ports that they use to connect routers to other telecommunication gadgets. For example, the connection to a wide area network requires the use of a serial interface to connect to a communication carrier such as the Sprint, the MCR. These are different telecommunication. Okay. Now, the data speed for the serial communication ports or routers are typically much slower than the data speed available on the internet. So, for the serial communication port, the speed they have on the router, they are slower than the fast Ethernet, the typical fast Ethernet, the gigabit Ethernet. Okay, so we've talked about this range. The range of the data speed for the serial port on the router are selected from maybe like 2500 bit per second to 4000 megabit, 4 megabit per second, or even higher data rates. Okay, so you can see there are high serials, the serial speed communication links, they are not so high. Their speed are not so high. But although we have higher one up to 8 and so on and so forth, that we will treat in the next chapter. So this one there is, you can see a router connects different LAN, different local area network. So the job here is to show how layer 3 switches called the router can be used to connect different LAN, interconnect different LANs together. Okay, the subnet mask is used. The subnet mask is used to determine if the data is to stay in the subnet we calculated earlier on is used to establish if the data will stay in the LAN or it will be forwarded to the default gateway provided by the router. Now the router uses its subnet mask to determine the destination network address. We've already established all of this fact. Now the destination network address is checked with the router's routing table to know or to select the best route to the destination. So we've established all of this, okay? So with this, we've come to the end of today's class. Thank you. Thank you for joining us and thank you for attending.